So, welcome back and good afternoon to all of you. Now, I would like to invite our speaker, Dr. Rajeev Anand Sahu, Post-Doctoral Researcher at the University of Luxembourg. Dr. Sahu received his Ph.D. in cryptography from NIT Allahabad in 2013. He has worked as assistant professor at CR Rao AIMSCS, University of Hyderabad Campus, and as postdoctoral researcher at the University of Brussels, Belgium. Currently, he is working as a postdoctoral researcher at the University of Luxembourg. He is a co-author of book Introduction to Cryptography. His areas of interest are digital signature, searchable encryption, and post-quantum cryptography. He has supervised Masters and Bachelors projects in cryptography in India, Belgium, and Luxembourg. He has around 2 dozen published papers in conferences and reputed international journals. So now I would like to request Dr. Rajeev Anand Sahu to deliver his lecture on elliptic curves in cryptography. Sir.
Thank you very much. So I hope I am audible.
Yes,
Sir,
yes.
can you please check if okay. So first of all, I am really grateful to Dr. Ratnesh Mishra and all the team members of AESS workshop, in general NIT Jamshedpur, are inviting me to participate in this workshop as a speaker. I also welcome all of the attendees of this talk, and I will be really glad if someone can find any motivation for his future research direction from this talk. So let's start this talk. In the coming next 1 hour, we will be moving in the world of elliptic curve cryptography. So I hope, as all of you have already a sound background in mathematics, and maybe in your technical life, you have already heard something about cryptography here and there. So maybe you have heard, I'm not sure how much you know or not, but knowingly or unknowingly, actually, we use cryptography in our daily life. So as soon as we send a message on WhatsApp, we swap our credit card or ATM card or any smart card. So we are actually using some kind of cryptography. So this sounds very interesting that it founds very sound application from algebra, and it founds its roots or origin in algebra. So it would be interesting to look. I think we can start with nice motivational example. So how about starting with a canonical cannonball puzzle? So we have a problem to solve that we have the set of balls, cannonballs. We want to arrange these balls in a three-dimensional pyramid, having square number of balls at every layer. So on the top we will have one ball, on the second level we will have two square, that is four balls, on the third layer we will have three square, that is nine balls, and so on. We'll keep doing. And we also want that at the end we should stop at the height where the total number of balls is also square in array, meaning to say that if I push this stack of ball from top to bottom and arrange it in array on two-dimensional, it should also count a square number of balls. So what exactly we want to do mathematically, if you see, so coming from top to down, we have at every layer we have square number of balls. So we have one square at the top level, two square at the second level, three square at the third level, and so on. So to solve this kind of problem, suppose we need to go until x number of layers. So height of this pyramid would be x. So we have total number of balls in this form, that is x times x plus 1 times 2x plus 1 by 6, which is a cubic equation in x. But at the end we also want that when we push this from top to down and array this only on two-dimensional, array these balls in 2D, it should also be a square number of square in number. So it should also be square of some variable, say y. So essentially we are looking for some equation which is cubic in one variable and quadratic in another variable. And this kind of equations have a graph or real number like this. So we have a pictorial presentation for such kind of curves, which is cubic in one variable and quadratic in another variable. We are looking for such kind of curves, or graph. So we can solve this, if we are really interested to solve this problem, we can solve it further. Like we immediately see that 0 0 and 1 1 are the trivial roots of this equation, and then having these 2 points, we join these 2 points, which is a line y is equal to x, and if we replace this y by x here in this equation, we can have a polynomial in x, and then by following the Diophantous method in theory of equation, we can keep solving that. We have two roots, so the third root will be, so we will have addition of roots that will be equal to the coefficient of second highest degree term in polynomial. Like this we can keep going and we can find the solution of this equation. But at the moment we do not focus on the solution of this equation, but we want to constrain ourselves in the world of polynomial in this family of curves, where we have a cubic equation in one variable and quadratic equation in another variable. One such type of curve is a generalized Weierstrass curve. So we have cubic in x, you see, and we have quadratic in y, and we have several other constants in this polynomial. Now let me try to boil down this equation in more simpler form. So we particularly wish to write this equation in a simpler form, having some square elements. So for that we have rearranged these terms, and we can do this only if we are working on some field for this elliptic curve which do not have characteristic 2, because we need this term, some a plus b plus c square. So we will have terms like 2 times ab, so we don't want the characteristic to be 2, so that we have facility to write these equations in this form. So further we have rearranged this equation in this way, which we can write by change of by representing this first term y plus a1x by 2 plus a3 by 2 as considering it as y1, and like other constants on the right hand side. So we have another form of the same equation. Further, if the characteristic is also not 3, then we wish to write this equation again in terms of some cube. So we change the variable. For x we do x1 minus a2 prime by 3, and we try to write this right hand side again on the cubic way, and then we come down to this kind of equation. For some variable y1 we have y1 square, and some variable of x1 which is x plus a2 prime by 3 we have x1 cube, and then some constants a and b, and we have this form of equation. This particular form of equation is called Weierstrass normal form for an elliptic curve. So we are actually interested to look in this kind of curves and their solution. These points x and y and also these constants comes from some field. So in general they could be complex field, real field, or rational number, but in cryptography we are more interested to have those points from some finite fields like multiplicative groups, a finite field of type fp or fq, where p is the prime, or q, it can be q also, which is prime power. So in particular, yesterday you had a talk on AES based on Galois field. So in the for the real application of cryptography, we particularly choose this q to be 2 to power n. So we work on Galois field. Okay, so here are some basic definitions and notations we are going to use in elliptical cryptography and in this talk also. So we have a curve of this form, which is quadratic in y and cubic in x, and the roots of these equation we collect and say the set of this set of such roots, we represent the set of such roots as ek, where k is the field from where we take our x, y, and the constants. So collecting all such points, we form a set, and with an additional point which is called point at infinity, or a special point, which works for identity element when we wish to form a group. We see discriminant of this curve is 4a³ plus 27b square. We do not want discriminant of our curve to be 0, otherwise it will be singular. We want a non-singular curve, so we want to avoid a shape like cusp or node for elliptic curve. So we don't want to consider a curve with this discriminant to be 0. So we want distinct roots. Let's have another look to different other curves of this form. So you see y square is equal to x cube minus x has this representation. Similarly, another curve of this form, x cube minus x plus 1 have this representation, you can immediately check that 4a cube plus 27b square is not 0. So they are non-singular smooth curves. Okay, now the question is how many points will be there if we count the roots of these elliptic curve or some finite field. So let's have a look on this. So since we are working on FP, the finite field, we have maximum p choices for x. Okay, that is p at post p values for this right hand side part of the equation, x cube plus x plus b. That means we have p values for y square, because this x cube plus x plus b is y square. But since these p values are for y square, for each y we will have plus y, for each y square we will have plus y and minus y. So we have two choices for all these values. So we have at most two p point. But then you remember we have also point at infinity. So we have total 2p plus 1 elements in EFP. This is the maximum possible elements we can have as roots in this set of elliptical group. But in FP, we have only p minus 1 by 2 squares number and p minus 1 by 2 non-square numbers. So we again boil down to half of this number. So instead of 2p plus 1, it is actually p plus 1. This is just an approximation. This is not the exact value of the roots or number of elements in elliptic curve group. Rather, there is a tight bound which gives an interval for the total number of elements of elliptic curve, which lies between p plus 1 minus 2 root p and p plus 1 plus 2 root p. So this is an interval in which the total number of elements of elliptic curve lies. There is more particular algorithm known as SEA algorithm with this complexity, polylog complexity, which gives total number of points in elliptic curve. But for certain elliptic curve, in general, for any elliptic curve, in my knowledge, there is no known algorithm which gives the total number of points in general for any elliptic curve. We work for different individual elliptic curves, but in general, we have a bound in which we can see what would be the range of total number of points of elliptic curve. Okay, let's do quickly an example. So in our example, we consider an elliptic curve. Y square is equal to x cube plus 4x plus 6. So you can see we considered a is equal to 4 and b is equal to 6. We are working on F7, so we are working modulo 7. So we try to find the roots of this equation. So when we try 0, when we put x is equal to 0, y square is equal to 6. So we don't have any element in F7 for which if we do a square we get 6. So we discard that point. So let's try with 1. So when we put x is equal to 1, we get 1 cube is 1 plus 4 plus 6, that is 6 plus 5, that is 11, modulo 7, it is 4. So we get y square is equal to 4. So we can see that for 4, we have 2, which is square give 4. So 2 square is equal to 4. But you see, since this elliptic curve has y square, that means this is symmetric to x-axis by the concept of theory of equation and curve tracing. So this is symmetric to x-axis. So as soon as we have some value for x, for y, like 2, we should also have the value minus 2, which satisfies this curve. So we have 1 comma 2 first point, but we should also have 1 comma minus 2. But minus 2 modulo 7 is 5. So we have these 2 points. So the points in elliptic curve always comes in pair because it is symmetric to x-axis. Similarly, you can keep trying putting x is equal to 1, 2, 3, 4, 5, 6 until 6, and you find these several different points. When we count these points, we have 10 points. But we remember that we have always an additional point at infinity that works for identity to make this as a group. So we have total 11 points. I would suggest you students to change to work to try this example with different p 11, 13, 17 and keep computing the elements of elliptic curve and see how what are the total number of elements. Okay, then we come to the algebra of this curve in order to realize it as a group. So when we have 2 points, P1 and P2, for which we have coordinate say x1 comma y1 and x2 comma y2, to add these 2 points and to find the third point P3, that we say let x3 comma y3, this is given by x3 is m square minus x1 minus x2 and y3 is m times x1 minus x3 minus y1, where m is the slope of the line joining these 2 points P1 and P2, and then we have already 2 points. Then again applying the Dafentas rule in theory of equation, we can realize third point and so on. So I won't go in detail, you can follow. But this is how we add 2 points in elliptic curve. Okay, what happens if these 2 points are same? So if P1 and P2 are same, say it is P1, so we have only one coefficient x1 comma y1, one set of coefficients. So to join two same point, that is point doubling, this slope won't work because it will be like a tangent at that point. So for that sake, we have this equation. You see y square is equal to, yeah, we have this equation y square is equal to x cube plus ax plus b. So to get tangent, we differentiate it to find dy by dx. So for this, we find dy by dx to be 3x square plus a by 2y. And at the point x1 comma y1, this will be in particular 3x1 square plus a by 2y1. So this will be our tangent, and then replacing this tangent in the previous value, we get x2 is equal to m square. It was minus x1 minus x2, but we have x1 and x2 same, so it will be m square minus 2 times x1. And y2, we had m times x1 minus x3, but here our x3 is x2 because x1 x2 were same, so it will be m times x1 minus x2 minus y1. So these are how we get the third point on the curve. The graphical representation for point addition would be like this. So you can see that there are 2 points P and Q. When we join these 2 points, it goes to R, and then we take its reflection according to reflection on x-axis, and we call it R prime, which is actually P plus Q on this curve. So you see, it satisfies the closure property because the third point is again on the curve. Similarly, we can check other properties like associative. We had already point at infinity as identity. We also know for any point x comma y, we'll also have x comma minus y. So we always have inverse of the point. So we can slowly check that whether it satisfies all the properties to qualify as a group or not. When we add two same points, that is, we are adding here P with P. So we have point P, and we join it with P, and then we make the straight line, which will be again tangent on P, and this cuts on a point R, and we take the reflection of R as R prime. So this blue point will be addition of P plus P, so that will be 2P. Similarly, we can see when we add 2 points P and Q, where Q is actually minus P, so it has quadrant x comma minus y. So in this case, you see we have a straight line. This seems some line like x is equal to a, some constant, and it will be a vertical line. So it will meet at infinity the point of infinity or identity point. So it will be equal to P plus Q is equal to identity. And if we even after that, if we take reflection to that point, on the other side, again it will reflect on the point at point of identity, point at infinity, which is at infinity. So we have different addition for distinct points and the same point at different location of elliptic curve. This is how we realize, and we can see if we are adding 2 points at the x is y is equal to 0, then we have this also. It meets at point at infinity, that is identity point. So 2p is equal to 0. So we have these things, these addition rules. Now we can quickly look to an example where we are working essentially on F13. So we have modulo 13 computations, and we have considered an elliptic curve x square is equal to x cube, y square is equal to x cube plus 3x plus 8. Let me consider 2 points P 9 comma 7. So x1 is 9, y1 is 7, q to be 1 comma 8. So x2 is 1 and y2 is 8. The first thing we need to do is we need to find a slope, that is y2 minus y1 by x2 minus x1. So we see this is 1 by 5, that means 5 inverse. In F13, 5 inverse is 8. 8 plus 5 is equal to 13. Okay, so we already have the values how we compute the third point, x3 and y3. So we do this m square minus x1 minus x2. So we have m8, so m square will be 64, minus x1 minus x2 will be minus 9 minus 1, so this is 54. Doing modulo 13, it will be 2, because 13 into 4, 13 times 4 is 52. Similarly, we will have the point y3. Okay, so this is going to be 10. So we have 2 new points, means 1 new point with two coefficients in x and y, 2 comma 10. So this p plus q, that is 9 comma 7 plus 1 comma 8, in the elliptic curve, x cube plus 3x plus 8 is equal to y square, computing over f13, that is modulo 13, we will get the third point, that is 2 comma 10. So this is how we do point addition in elliptic curve. We have another example. If we want to do doubling, that is we want to add a point with itself. So we can also see in this case we essentially compute dy by dx, which is given by 3x square plus, we can see what is the value of, so this is 3x square plus a by 2y. So doing that, 3x square is, our x1 is 9, so 3x square is 3 times 9 square plus a is 3 in the equation, x cube plus 3x, so a is 3 by 2y, so y1 is 7, so 2 times 7, and similarly we can do all this further computation on modulo 13. Every time we apply modulo 13, and we get these 3 point, the next point that we call say x3 comma y3 as 9 comma 6. This is how we do doubling. So in this way, in general, if you want to summarize this thing, to compute np, so to make n times addition of some point, so we have a point on elliptic curve, we want to add that point n times. So for this, we exactly do not need to do n times addition. Instead, we have something like this square and multiply thing here also in elliptic curve, which we call double-ended algorithm. So to realize n times p, when n is even, we do it in this way. And when n is odd, we take the floor value and plus p, we do it in this way. And combining these two things, we can compute any n times p. What is the advantage of this thing? So the advantage is that we need not to do n times addition, but we just need to do only log n doublings and at most log n addition. So let's log n doubling, log n addition means, for example, we need to do 8 times p, so it is 2 cube p, so log will be 3, so we need to do maximum 3 times doubling. You see, p plus p is equal to 2p, so one doubling, 2p plus 2p is 4p, second doubling, 4p plus 4p is 8p, so third doubling. So 8 is 2 to power 3, so log of this will be 3, so we need to do maximum log n doubling, otherwise we have to do 8 times addition, so that reduces the complexity. We have an immediate example. For example, if you want to compute 947 times addition of point P, you can see the maximum number of doubling in this point, in this computation is 2 to power 9. So we need to do at most 9 doublings, and then we need to do 6 additions. So in total, to realize 947 times P, we need to do only 15 point operations. So you see how concretely it reduces the computation. So this is a quick background on elliptic curves, which would be good for understanding the overall idea of elliptic curves in cryptography. So from here onwards, I will be moving slowly towards cryptography, and we'll try to see how these computations on elliptic curve helps us in realizing different cryptographic primitives. So for this motivation, let us start with at least two hard problems. So we know what is an integer factorization problem. But here I would like to focus all of you in two other important problems. Those are discrete logarithm problem in discrete groups, which is for if we have a cyclic group G and we have an element H of that cyclic group, then to compute an integer x such that G to power x is H, and we'll work modulo, if our group is like filled FQ, we will work modulo Q like this. So to finding this element X is really a hard problem, which is known as discrete logarithm problem, because this X is known as discrete logarithm of H. We have a counterpart of this example, or we have a replication of this problem or elliptic curve. So when we want to realize the same problem on elliptic curve, previously we were working on the multiplicative group, so we had G to power X, so we are multiplying G X times. Here this elliptic curve we are considering the addition operation, so we have additive group. So in this, the same replication of this problem is by realizing an integer X, for which we can have X time P is equal to Q, where P is the generator of elliptic curve like G there in the previous problem, and Q is some point in the elliptic curve. So to realize or to compute this X, which gives us this relation, so that X times P is equal to Q for any point Q in elliptic curve, is known as elliptic curve discrete logarithm problem or insert EC-DLP. What is the advantage? Okay, so the advantage is that, so from here we are going to see the motivation of elliptic curve, why these elliptic curves are important in cryptography. So previously, before to this elliptic curves, in cryptography we were working in multiplicative group or finite fields, for which we had this discrete logarithm problem as a hard problem. But then for this problem we have certain methods like index calculus method, which can solve this discrete logarithm problem in sub-exponential time. So e to power root log n, like that. So we have sub-exponential time, which is, if not polynomial, then also at least not exponential. So not too much. If we can rearrange good supercomputers with certain parallel computing, this should be possible. So what this indicates? This indicates that for the required security, the keys, the size of key in bits should be very, very large. So this will slow the computation. This will affect our storage space, which we don't want. The alternate idea is to use elliptic curve groups, which actually give the same sort of security with very smaller group. And the other advantage of ECC is that, similar to this index calculus for DLP, now only now in last a few years there are also some sub-exponential time algorithm, but they works only for some specific curves with some certain restrictions. They are not very much practical and until only have the theoretical interest. So we are still good for those kind of hard problem in ECC, while in finite field we have a sub-exponential time algorithm. Besides this, when we use ECC, we can use really smaller parameter, which helps us realizing higher speed, lower power consumption. So it can work in a tiny processor devices like our mobile phone, either or some small gadgets, and this gives the bandwidth saving. This also secure the storage space, and it can provide smaller certificates bitwise. To understand more technically, we have different security levels in cryptography. So for example, the first row, 80, 112, 128, 192, and 256, they are level of security we want to achieve in any cryptographic primitive. So they are coming from the AES. So for example, we have 192-bit AES, or in very simple language for general understanding, we can say that when we say that some crypto system achieves 256-bit security, so in a general language we can say we need to do 2 to power 256 computation to break that crypto system, which is too large. You see, 2 to power 10 is 1024, and when we go 2 to power 11, just one more, it is 2048, and keep going on. So 2 to power 256 is beyond any computer in this world at now. We see, to achieve this security in RSA, our group should be, the group of integers should be of 15,360 bit, you see, which is very large group. And if we use this group, the simple computer should be very slow. It won't work efficiently. Instead, in elliptic curve, we can only use a group with 512-bit elements, which is, you see, cubic or very small, reduced in size compared to the size of groups in RSA or any crypto systems which use DLP. So this is a biggest advantage using ECC with compared to other existing classical crypto systems like RSA or LCMR, which based on the different set of integers with larger bit size. So we had already seen what an EC-DLP is. This is realizing an integer n, for which we can have q is equal to n times p, where p is generator of elliptic curve and q is some point of elliptic curve. We can see that these, when we have the roots of this equation, it satisfies this property, closure, associativity, identity, inverse. In fact, it is an abelian group. So we have a nice structure of group now in which we can pick our public key or private key, or we can see if everything is happening in cryptography. So to realize a cryptographic primitive, a public key cryptographic primitive, we usually check that whether there is something called a Diffie-Hellman key exchange protocol, which is a protocol between two users who want to exchange their keys before the actual communication or actual encryption or signature. So how this should be possible on the public domain, that means over the insecure channel, so that both of these users can exchange their values and can compute something which can be secure or hidden from anyone who can have access to that channel. So On the elliptic curve version, we can see that. So let's consider there are two users, Alice and Bob. They both agree on a finite field Fp, and then they realize the elliptic curve over this Fp. So we have an elliptic curve. This would be some sort of curve like y square is equal to x cube plus 7x plus 3, like this. So they already agree on some certain a and b and realize this elliptic curve. Then they have generator of this elliptic curve p, capital P. Now Alice has a value, an integer. Alice randomly selects an integer a from the q star, sorry, and then Bob randomly selects another integer b. With these integers they compute a times p. Alice computes a times p. We know how to do this. This is just a times addition of p. We have seen how to realize n times p. And Bob computes b times p, and this small a and small b are private keys, are private values which are known only to them. Computing this capital Q and QB, which is A times P and B times P, they exchange these values. So they are exchanging this value. That's why we call it key exchange. So they exchange these values. So Alice gives this capital QA, but not the small a, to Bob, and Bob gives this capital QB to Alice. So now Bob has A times P, and he already has his private value B, which he can multiply with A times P. So it will be ABP. Similarly, Alice has this capital QB, which is B times P, and he also has his private value A, which multiplying with BP will be again ABP. So at the end, they share the same value, that is ABP, while anyone else who can only see this QA and QB but do not have access to small a and small b cannot do this. So we can do this thing very securely for a public channel. This was a breakthrough in cryptography in 1976 by Whitfield Diffie and Martin Hellman of MIT. So after their name, this is also popularly known as Diffie-Hellman key exchange protocol, or in short DHKE. This gives rise to digital signature algorithm. Why? Because for public, we can have something private using which we can share some public values and then can realize some values based on our private values. So this gives rise how to share things or public domain. So this gives rise digital signature. Based on this philosophy, based on this technique, there is something called a digital signature algorithm, which is realized in finite field, a multiplicative group. But then there is elliptic curve version of the digital signature algorithm, which is now considered as a standard signature to use a digital signature in many platforms. For example, when we have these Bitcoin transactions, you might have heard about blockchain technology, which is a public ledger over which we can do transaction of virtual money, which are called Bitcoin or Ethereum or Zcash. So for authentication, we need a digital signature where we use actually this elliptic curve digital signature algorithm, that is ECDSA, in several security services in America and worldwide. This standard signature scheme is used there. So let's have a look to the algorithm, what this algorithm says, and we'll also keep our eye that what this basic idea of elliptic curve, where does it help? So in setup, you see we have a prime P, then we have elliptic, we can realize elliptic curve over this field Fp. We have also a hash function here, which is a compression function, which convert an arbitrary length bit string to a fixed length bit string. So here you see it converts an arbitrary bit string to a length with a floor ceiling size of log q, so a fixed size. Then to generate the key, the user randomly selects an integer a and then compute a times p. This a is known only to the user. And then in digital signature, there are essentially four main algorithms. So first is setup, where we have the basic setups, what kind of group we will be using, what kind of functions we will be using. Then the second algorithm is key generation, where we see how these users would generate their respective keys. The third algorithm is signing or signature algorithm, where the user having the private key will generate its signature. So here we see the user had selected A, so we'll see how he will be using this A. Now to realize a signature, the user select a random integer K between 2 and Q minus 1, because if you do 1 times P, it is P. So then he computes K times P. This we know how to compute this. Computes U is equal to X modulo Q, so which is actually X quadrant of this Kp. So in Kp we have x comma y. We have seen at any point on elliptic curve we have x comma y. So this is the first quadrant of this point Kp, which we call x, and then he also computes v, which is a h plus a times u, and then k inverse. So this h is has of m. The message we have, for the message we can have a bit string, and then we have the hash function in which we convert this bit string to a fixed size of ceiling log q. So that is our h. A is the integer, u is the x of the point Kp, and k is the integer for which we can realize an integer, because this we are doing it zq zq. So we always have inverse of this. So this way the user actually computes small u and small v, which he calls signature on the message m, and he sends this signature, which is u comma v, to the recipient of the signature, or to anyone he want to send. Receiving this u comma v, the verifier first computes this hash, the message digest, that is h of m, and then v1 and v2 after that, which is h times v inverse. So we see what was v. So v was basically a value in gp, so we can compute this v inverse, and with this v inverse we compute v1 and v2, and having this v1 and v2, then the verifier computes v1, which is an integer, so v1 times p, where p is the point of elliptic curve, and also v2 times q, where q is also point of elliptic curve. This comes by using double-ended algorithm, and then he verify. So basically this right hand side value v1 times p plus v2 times q is actually a point on elliptic curve, because it is closed with this addition, satisfying the closure property. So in that point we just consider the x quadrant, and we see that if this x quadrant is equal to u, the first quadrant of the signature, or not. If so, then he validate the signature. If no, then he discard the signature. I have a small example to do on ECDSA. So we have an elliptic curve x cube plus x plus 6. We want to work over f11, so modulo 11. And then we have the secret, the Alice select, let he select 7, and then he publishes the verification key q, which is q, so which is 7 comma 2. To sign a message m, let me consider the hash value of the message is 4, following some standard hash function. Then he choose the random integer 3, compute 3 times p, where p is 2 comma 7, so 3 times 2 comma 7 is 8 comma 3. This we know how to compute, and then considering its x quadrant, it will be 8, so small u is 8. Similarly he compute other values, and for small v we have 7, so finally the signature would be 8 comma 7. To verify, the verifier has to compute h v inverse, so our v is 7, h was 4, so 4 times 7 inverse, 7 inverse in 11. Okay, we can see, and then this would be the value, 4 times 2 is equal to 8, and v2 is equal to 3. So the signature would be so the signature is valid because this we can see what is the value of v1 times p plus v2 times q, that is 8 comma 3. So the x quadrant of this point is 8, which is exactly equal to small u. So this is how we validate the signature. Then at the last, I would also like to just include some applications of elliptical cryptography, but it is not limited only to this. So this elliptical cryptography is very, very practical and useful in real electronic communication or transactions, where all the key exchange we do with any devices with tiny processor, for example our phone or smart card, the key exchange happens by means of elliptic curve Diffie-Hellman key exchange protocol. And as I already mentioned that when we need to do a transaction of some Bitcoin over public ledger of blockchain, we need a digital signature. So what we do essentially on blockchain, so we have block of hashed messages in which the user or the sender who wants to pay a Bitcoin to a recipient first put the amount, how much amount you want to pay, realize its hash value, then he put his digital signature, which is realized using elliptic or digital signature algorithm, so ECDSA, and he also put his public key, and then he put everything and has this value in block and send this block to the recipient. Receiving this block, the recipient first verify whether this comes with a legitimate source. So he actually verify the signature with the public key of sender, and in this algorithm, this ECDSA is used. For practical purpose, usually this 25519 curve is used, which is value of the prime 2 to the power 255 minus 19, this prime on which we realize the elliptic curve and do the computation. In the Bitcoin, in the blockchain technology, we specifically use this ACCP 256 cable elliptic curve. So this is quickly all about the use of elliptic curves in cryptography. Thank you very much for your attention.
Ah, thank you, Rajiv.
Okay, sir.
So thanks for your beautiful and motivated talk, especially started from cannonball puzzle. It's a very interesting example. And also you have presented elliptic curve in cryptography in the very fashionable way. So again, my sincere thanks to Rajiv for your spending valuable time for this workshop. It will really very helpful for our participants. So now I'm requesting to the participants, if anyone have a query, so please you unmute your mic and ask the question from our speaker. Okay, so sir, man, sir.
Thank you, sir, for this interesting talk. And participants, we will now meet again at 4 p.m. for the next lecture. Uh, okay, so there will be a break till then.
Yeah. If anyone have any doubt, they can still email me. I would be happy to receive your queries and to respond them if I know or if I can know to best of my knowledge. I am open for the queries anytime, any day. And I thank again all the team of AASE who worked really hard to realize this very nice concept of workshop on the application of algebra, because I see the algebra is a kind of mandatory course in mathematics in India and everywhere in the world, but it is rarely realized that what are the real application of algebra. We only see lots of theoretical theorem or notions, but to know their applications really inspire the student to realize any research direction on algebra. So I really found this program very nice and helpful for the student. My best wishes to the students and sincere thanks to all the organizers and the team. Thank you.
Okay, thanks, Rajiv. Again, thanks for your beautiful words for our workshop. Thank you very much.
Thank you, sir. Thank you.
All right, guys. I hope you can hear me. Sorry, guys.
Yes.
Okay, guys.